Hello everyone. In this video, I am going to explain about the voltage regulators. Especially the voltage regulators are very important when we design some circuits. Here is the basic type of regulators. Initially, the regulators can be divided mainly into two groups, linear regulators and non-linear regulators. Under the nonlinear regulator, it has again three groups: Zener diode resistor base, Zener diode transistor base, Zener diode transistor and error amplifier base. So first, let me explain the Zener diode resistor based regulators. So here is the simple schematic of the Zener diode resistor base regulator. So we can just say that the Zener diode based, okay? To implement the Zener diode based regulator, we have to use the resistor and Zener diode connected in series. And here is the load resistor that should be connected in parallel with the Zener. So all symbols have own meaning as I mentioned here. So since we have connected the load in parallel with the Zener diode, the load voltage should be equal to the Zener voltage. Here is the IS. IS has two parts, IZ and IL. So now we can obtain the expression for the IS, which is given by Vs minus VL divided by Rs. Rs is the resistance of the source. So here is the expression for the load current given by VL divided by RL. So according to this schematic, we can also write an expression for the IS. IS given by IZ plus IL. So now we can add the equation number 1 and equation number 2 into the equation number 3 to obtain the expression for the IZ, which is given by this one. So we need to understand, in order to maximize the load current, we have to reduce the Zener current. We can obtain the maximum load current at the time when the IZ becomes 0. So now the maximum load current equal to the voltage difference Vs minus VL divided by RL. Here is the variation of the load current. It has upper boundary, which is the maximum load current given by this equation. So the current can change from 0 to that upper value. And also we can obtain the minimum load resistance, the minimum load resistance, which is given by this expression. So the load resistance also has the range that can start from the minimum value, then it can go for very large amount of value. An example. So now I have selected 30 volt for the Vs, 10 volt for the Vz, and 20 ohm for the Rs. As we know, Vz equal VL, which is 10 volt. Okay. So then we have to calculate what is the maximum current. What is the maximum current? So we just need to add this value into this equation. So Vs 30, VL 10, Rs 20. So then we will have 1 ampere. So then we can calculate the minimum RL. To calculate the minimum RL, we can use this expression. According to this expression, so minimum RL can be calculated as 10 ohm. Okay, the maximum current 1 ampere, minimum RL 10 ohm. So now we can go for some simulation. Here is the simulation result and the related schematic. So I have used that minimum RL value. Here is the minimum RL value. So here is the source voltage, which is 30 volt. This is the Rs, which is 20. Diode has 10 volt. 10 volt is the breakdown voltage of the Zener diode. After drawing this schematic, so in here I have simulated. So simulated graph shows the variation of the load voltage as the function of source voltage. Here's the source voltage. So that can change from 10 to the 60. So now we can see that this is the 30 point where we have selected the value for the theory. So here is the 30 volt. When the Vs equal 30, so what is the load voltage? So here is the load voltage. See, the 10 volt, which is correct because as I mentioned, the load voltage would be equal to the Zener voltage. Here is the Zener diode. It has 10 volt. So then almost equal. Okay. So now let's go for the simulation when the RL becomes less than this value. So now I'm going to select 8 ohm for the RL, which is less than the minimum value. So in here you can see source. This is the voltage related to the voltage source. In here you can see that the load voltage, which is now 8.6, less than the expected value, which is 10 volt, which means now this circuit, now this regulator doesn't work, cannot be maintained at the regulated voltage, which is 10. Here is the advantage and disadvantage of Zener-based linear regulator. The advantage, you already saw that the circuit is very simple. So it has simple circuit diagram and also low cost. Good as the voltage reference. This is another advantage. Good as the voltage reference, not the current. So it has also disadvantage. Temperature dependent, which means that when the temperature goes high or goes down, the Zener voltage cannot be maintained. The disadvantages be high power dissipation. As you know, here is the structure. When the load needs a very large amount of current, that current should come through the RS, How current comes to the RS means there will be some power dissipation to the RS. Since the currents become very high, the power dissipation also becomes very high. So now let me explain the second type of linear regulator, which is Zener diode and transistor base. So here is the simple schematic of the Zener diode transistor base linear regulator. So this one comes from the previous one, the simple structure, only Zener diode base. So for this circuit, why we are using this structure, which provides the voltage reference for power switch, this transistor. So depending on this value, it can control the current. But here, Zener voltage, which is almost constant, okay? Here is the basic expression for this circuit. So, so I believe that you can derive this equation. So first let me explain the IS equal IZ plus IL. So IS equal IZ plus IL. So here you can see IS means the input current, so which is equal to these two portions, IL and IZ. And here, so then I just need the current for the IL, which is given by IS minus IZ. In here, IZ means the current through the simple structure given by the IS and Zener diode connected in series. We can get the voltage reference Vs minus Vz and divided by Rs, which gives the current through the Zener diode. And so here is the load current, which is given by VL divided by RL. But the special thing is, this kind of regulator, we can write the expression for the VL only using the VZ and VGS. VGS means the voltage between the gate and source. So here is the expression. VZ equal VGS plus VL. So now we can get the expression for the VL, which is given by VZ minus VGS. So here is the maximum current given by this expression, Vz minus Vgs divided by RL. So this difference equal to the VL, okay? You already know that. So then we can get the minimum RL. The minimum RL gives the maximum current through it. So minimum RL gives when the IZ equals 0, which means IS equal IL. Yeah, okay. So now, unlike the previous one, the IZ can be very small, and it can change to the very large value. And also the load resistor can be small, which is given by the RL min, and can change to the very high value. So let me explain the advantage and disadvantage of this type of linear regulator. So Zener transistor based, okay, it also can be low cost and simple. Disadvantage is temperature dependent. It cannot handle the variation of temperature. But we can ignore this one, high power dissipation, because previously the high power dissipation occurred through the RS. Now for this structure, we can select large value for the RS. So then which gives the small IZ current. So then there will be no power consumption. Actually, there will be very small power consumption compared to the other powers. But in here, still this disadvantage is remaining. Unexpected source load variation cannot be handled. In addition, we have another type of regulator, which is under the Zener transistor base category. Okay, so we call that type of regulator as shunt regulator. Here is the schematic of the shunt regulator. But in here, we have connected the transistor in series compared to the DS and VL. But in here, we have to connect this BJT transistor is kind of parallel to the VL and ground. So we can obtain now the expression for the load voltage, which is given by VZ plus VBE here. So this type of regulator has basically 4 current paths. IS is equal to the IZ plus IC plus IL. Here is the expression for the IS. So IS given by the difference between VS minus VL divided by RS. Okay. And we can get the expression for the IL, which is given by VL divided by RL. And also we need to know that we can write the IC current using the gate current, which is provided by the IZ. So now we have IC equal beta times IZ. The beta means current gain of the BJT transistor. So here is the expression for the maximum load current, which is given by VS minus VL divided by RS. So in that case, the maximum load current can be changed from 0 to that upper boundary. Now here is the expression for the minimum load resistance given by this equation. So the load value, the load resistor has this variation. It has some lower boundary, and the load resistor can change to the very high value. And here is the advantage and disadvantage of shunt regulator. The advantage is still low cost, simple, relatively high current handling. Compared to the previous regulators, this structure can handle relatively high current. Disadvantages: temperature dependent, high power dissipation. Now you can see the input current come through the RS. Come through the RS means there will be power dissipation through the RS. So high power dissipation. And also the unexpected source load variation cannot be handled. So here is the last type of linear regulator: Zener diode, transistor, and error amplifier base. So here is the simple structure of the Zener transistor error amplifier base linear regulator. So it has the simple structure, type 1 and also type 2, but additionally it has the error amplifier and voltage reference part. Here is the expression for the maximum current of the load, so which is given by VZ minus VGS divided by RL. So depending on RL, the values can change from very small to the very large value. Since we can select very large value for this RS, the IZ current will be very small. Okay, so in that case, we can say that RL nearly equal to the VS. R value can also be changed from very small value to the very large value. Let me explain the operation of the Zener transistor and error amplifier based linear regulator. So we need to assume that the current into the amplifiers are almost zero. The current into the amplifier are almost zero. So in that case, we can select the values of RS, R1 and R2 large. So then we can obtain the output voltage of the amplifier using this expression. So AV means the voltage gain. This difference comes from the VZ minus Vx. Now, what happens when the VL decreases? Little, okay? When the VL decreases. Since this voltage divider has been connected to the VL, when the VL decreases, Vx also decreases. But the thing is, Vz remaining a constant. Okay, so according to the equation number 1, this output of the amplifier start increasing to increase the gate voltage of the switch, this one. Then IL, this is the IL increased to maintain the VL again. Then the IL is increased to maintain VL again. That's how this works. So here is the advantage and disadvantage of Zener transistor error amplifier based linear regulator. Advantage is an accurate regulator, but the disadvantages are complicated, relatively expensive. Thank you. During my next video, I will explain about the digital regulator. Actually, digital regulators are a little bit complicated compared to the linear regulators. Thank you.